So, good morning and welcome to this Licentiate presentation where Mr. Robin Forsling is going to present and defend his dissertation, Decentralized Estimation using Conservative Information Extraction. My name is Anders Hansson. I'm going to share this session. I'm Professor of Automatic Control and I will also be the examiner. Before we start, I would like to mention that this is a recorded Zoom seminar. Other people involved are the opponent, who is Dr. Benjamin Noack from Karlsruhe Institute of Technology. Very welcome to this seminar. Others involved are the supervisors, Professor Fredrik Gustafsson, Dr. Gustaf Hendeby, and Dr. Zoran Sjanic. The procedure is the following. First, Robin will give a presentation, which is about 30-40 minutes long of his work. And after that, the questioning session will start by the opponent. And after that is concluded, which will take about an hour or so, we will open up for questions by the audience using the Q&A features of Zoom. And after that, I will meet with the opponent and with the supervisors, and I will decide about the grade, pass or fail. And then we will get back into this Zoom seminar and announce the outcome. So with this, I would like to leave the floor to Robin, please.
Thank you, Anders. So I just want to add that this work has been supported by Licentiate and Saab. So we start directly with a motivating example. If we look at this figure, we have multiple agents, where each agent has its own sensor. Measurements from the sensor are then pre-processed into what is called estimates, which contain both the new and old information. These estimates are later exchanged using a data link, and both the pre-processing of information and the communication of estimates will induce dependencies between the estimates. Dependencies called cross-correlations. So in decentralized estimation, these are often, most often unknown, and there's a risk then to double count information, which will mean a risk to underestimate the uncertainty about, say, a target. So this is where conservative estimation comes in. So conservative estimation is about not underestimating the uncertainty. So the thesis is or can be separated into one part with unpublished work and one part with already published work. So in thesis chapter 3, we formalize the conservative linear unbiased estimation problem. And in chapter 4, properties of different conservative fusion methods are analyzed. Then we have chapter 5 and 6, which is adapted versions of two conference papers, both presented at Fusion. So starting with conservative linear unbiased estimation. But first, the classical linear estimation problem. So basic assumption throughout the thesis is that the data to derive an estimate from is given on the linear form, where y is the data, x is the true state to be estimated, h can be seen as the measurement model, and v is additive noise. The covariance of y is given by r. So in linear estimation, the estimate x hat is calculated linearly from the data. The unbiased constraint means that the expected value of the estimator equals the true state, which is equal to saying that k, the estimation gain, times the measurement model should be identity. But we don't only want to calculate a linear estimate and an unbiased estimate, we want the optimal estimate. So then we formalize this into the following optimization problem, where argmin means we minimize p with respect to k over the subject to the unbiased constraint. And it is well known in linear estimation theory that the solution is given by this k star, which is the weighted least squares approach using R inverse as the weight matrix. And this estimator is called the blue, which is the best linear unbiased estimator. So often it's very useful to represent covariance matrices as ellipsoids, or ellipses as they are called in 2 dimensions. So here we have 2 ellipses, one for R1 and one for R2, and we see that R1 strictly encloses R2. Then we say that R1 is larger than R2 in the positive definite sense. The inverse of covariance matrices are called information matrices, or simply information. And we see that if R1 is strictly larger than R2, then R2 inverse is strictly larger than R1 inverse. So it's, especially in conservative estimation theory, it's very useful to use the information representation. So what do we mean by unknown cross correlations? Well, say that we have some data, y1 and y2, which we stack into a larger data vector y, still given on this linear form. Then the covariance matrix of y can be expressed as a 2 times 2 block matrix. And when we say that the cross correlations are unknown, we mean that this block R12 is unknown. So then we don't have all the data necessary to compute an estimate. So how do we do it then? Well, our first step is to model R as belonging to a set, this fracture R, which I will just call the R set. In general, this contains infinitely many covariance matrices, which R can potentially be. The problem, however, we have no clue for which element in this R set equals the true covariance R. So the solution is then to, of course, get a clue, where the clue is the conservative linear unbiased estimator, which is an estimator which, apart from being linear and unbiased, also is able to guarantee that the true covariance, here given by cov of xz, is bounded from above. And this criterion is equal to saying that P must be larger than all the possible quadratic forms here expressed at k r prime k transpose, where r prime is an element in the R set. So geometrically, this means that if P is the covariance matrix calculated by the estimator, this ellipse has to enclose the true covariance ellipse. And this is then the most important part of conservative estimation, to ensure this. But we also want, like in the linear estimation case, to minimize how much we overestimate the true covariance. So this leads us to the following optimization problem. To the left, we have the classical linear estimation case, where we know that the solution is given by the blue. To the right, we have the conservative linear estimation case. Here we see that we have to optimize over 2 variables, not only k as in the other case, but also p, since we don't have access to the full and true covariance R. The optimal estimator in this case is called the best clue. But finding this best clue might be difficult, so therefore we propose a restricted optimality criterion. So we say that we want to calculate P as a quadratic form, similar to the classical linear estimation case. But instead of using R, we use this R bar, where R bar is a so-called conservative bound. So it is guaranteed to be larger than all elements in this R set. And then we get a new set, this fracture bar R set, which I will just call the R bar set. And this set contains all possible conservative bounds. So then we end up with another optimization problem here to the right, where the solution is called the restricted best clue. And we see in this case that we can derive a closed form solution to a problem. which is identical, at least in structure, to the blue case. The difference lies is we use instead of R, this R bar star, where R star bar is the smallest element in this R bar set, and this does not always exist. So just a comment on the R bar star. When I defined this notation in the thesis, I did not think about the pronunciation. So it sounds a little bit ridiculous to say R star bar. But still, as we see in this figure, we cannot always find this minimum conservative bound, R bar star. So we can look at the smallest possible conservative bounds will be those bounds that intersect these 4 points of the dashed rectangle. And inside this dashed rectangle, all ellipses corresponding to the covariance matrices of the R set belongs. But we can't say that neither of these ellipses is larger or smaller than the other ones. But there are workarounds to this problem as well. So we can, for example, use a loss function, J, and minimize that instead, or parameterize these conservative bounds. So in this case, all the smallest ones, the ones that intersect these 4 corners, are given by the following parameterization, R bar of omega. So we now turn to the fusion case. Fusion is just another estimation problem where we merge estimators or estimates. We will only deal with linear fusion. I will change notation also to align the notation with the thesis. So instead of data y, we speak of joint state estimates, z hat j. R is replaced by Cj, which is the joint covariance. H is replaced by Hj, which can be seen as the joint measurement model. And we still have the linear model for the data. Just another notation. Also the sets, the R set is replaced by the C set, and the R bar set is replaced by the C bar set. So I will describe 3 conservative fusion methods, where each method is related to a specific correlation structure. Correlation structure can be seen as adding some knowledge about the unknown cross correlations, as we will see. And this knowledge will affect the C set and the C bar set. Having more knowledge about the cross correlations means that we can include smaller elements in the C bar set. So the first method is covariance intersection, which is related to the completely unknown cross correlations, which is just we don't have any structure at all about the cross correlations. The second method is inverse covariance intersection. Here we assume the so-called correlated information structure. At last we have the largest ellipsoid method, where we assume component-wise aligned correlations. So say that we want to fuse z hat 1 and z hat 2, where the corresponding covariance matrices are given by C1 and C2. Then we know that despite what the actual cross correlations are, the blue estimator, the covariance of the blue estimator, will have an ellipse that lie in the intersection of C1 and C2. So then if we can find a covariance that encloses this intersection, then we have found a conservative estimator. This ellipse is given by the following parameterization, which is a convex combination of the information matrices C1 inverse and C2 inverse. And it is shown in the thesis that the covariance intersection is the restricted best clue, given that we have completely unknown cross correlations. Turning to inverse covariance intersection, then we instead move to the information domain. So now I have plotted the 2 information ellipses. Inverse covariance intersection assumes correlated information, of which common information is a special case. So I will only show here the common information. In this case, it is assumed that the C1 inverse and C2 inverse can be decomposed into the common information, where the gamma inverse is the common information shared by the two estimates. So if this decomposition holds, then we know that the common information, gamma inverse, has to lie in the intersection of the two information ellipses. So then we can use what we know about from covariance intersection and simply bound and close this intersection. And this bound is given by the same parameterization as in covariance intersection. So when we have found this upper bound on the common information, we subtract it from the sum of C1 inverse and C2 inverse. Then we know that we have a conservative estimator, given that this decomposition holds. And it is also shown in the thesis that inverse covariance intersection is the restricted best clue given the correlated information structure. So the largest ellipsoid method also assumes the common information structure. But in this case, we instead calculate the largest information ellipsoid enclosed in this intersection, here given by the gamma LE inverse. And then if we move back to the covariance domain, we simply subtract this from the sum of C1 inverse and C2 inverse instead. And then we get an even tighter and even smaller covariance ellipse. So this is actually the largest covariance that is enclosed in the intersection of C1 and C2. And in the thesis, it is shown that largest ellipsoid method is the best clue given component-wise aligned cross correlations. So to summarize the conservative fusion methods, I have this figure. If we start from above, say that we have completely unknown cross correlations, then we know that the optimal conservative estimator is given by covariance intersection. But if we can include some more information about the cross correlations, like correlated information, then we can decrease the number of elements in this C set and include even smaller elements in the C bar set. And hence we can find an even tighter, an even smaller covariance bound. And in this case, the optimal conservative estimator is given by inverse covariance intersection. If we can include even more information about the cross correlations, like component-wise aligned cross correlations, then we can reduce the C set even more and include even smaller elements in the C bar set. And in this case, the optimal conservative estimator is given by the largest ellipsoid method. So I will now turn to the two conference papers, which both deals with decentralized fusion setups where the communication is constrained in some way. So in the first paper, we will deal with this so-called the diagonal covariance approximation. And this paper was presented at Fusion 2019. So first we start with an observation. We know that the covariance matrix C scales as n squared, where n is the dimensionality of the corresponding state. So this can be very bandwidth demanding, at least for high dimension. So one possible solution is to approximate C by a diagonal matrix D. And then we end up with being only required to transmit n parameters. There's a problem with this approach though. So say that we have this covariance matrix C, and we construct D by only taking the diagonal elements of C. Then D will not be larger than C, so we lose this conservative property. This can be illustrated as follows. So if C is given by this ellipse, then D will be given by this axis-aligned ellipse. And we see that D does not enclose C at all points. So this means that we have to recover the conservative property of the estimates in some way. And this brings us to the problem formulation to guarantee that conservative estimates given the diagonal covariance approximation is possible. So for this purpose, a couple of methods have been proposed, which I will describe now. So starting with the same example as in the previous slides, if D is constructed by picking out only the diagonal elements of C, then we can't be assured that D is larger than C. But say that one agent receives D from another agent, but know that there's some other underlying covariance matrix C, then this agent who receives D know that C must lie in this dashed rectangle. Hence we can use what we know from before, that if we enclose this rectangle, then we have constructed or recovered conservativeness again. And the required scaling for this is to scale D by the dimensionality n. And this is called the dimension-based scaling method. A more efficient way is to do the scaling at the transmitting node, since this node, of course, has more information about C. In this case, we can find this point x lambda, and by that calculating a scaling constant c lambda. And then we get a smaller information loss, since we can enclose C tighter. And this method is called the eigenvalue-based scaling method. Another way is to think of z hat as being n different independent estimates of different components, where each diagonal element of the diagonal matrix D is the variance of the corresponding estimate. Then we can directly adapt the general form of covariance intersection and just assume that all these zeros only means that the cross terms are unknown. And then we know that the fused estimate will be a conservative estimate, because covariance intersection is always conservative if the input estimates are conservative. Another way is to use the so-called optimization-based scaling method. So say that we have this D set, which contains all diagonal matrices. Then we optimize over some loss function J, subject to D being larger than C, and then we find the optimal upscaled D star. I now turn to the second conference paper, which was presented at Fusion 2020, which considers information selection methods, which is also a type of, or a class of methods to reduce the communication load in decentralized fusion setups. So the problem is formulated as follows: select and transmit only information that is useful for the other agents. So I will only briefly describe these methods. The first is called the largest eigenvalue method. This method makes an eigenvalue decomposition of the information matrix and then just picks out the most informative projections. The second method instead selects information based on previously transmitted information. So a bit more sophisticated method. And similar, the received information method select information based on previously received information. So all these methods, both in the DCA paper and the information selection method paper, have been evaluated, but on a simplified version of the motivating example we saw in the beginning. So in this case we have two cooperating agents, the blue circles, which moves towards a target, the red one. Each of the cooperating nodes or agents has its own sensor by which it extracts information using by measurements of the target. These measurements are then filtered in tracking filters, which are pre-processing units, into track estimates. Then these estimates are exchanged between the two agents. And here the transmitted data, which is transmitted over the data link, depends on the actual method from DCA or the information selection method. These communicated estimates are then fused using covariance intersection. So I will not show you any results from this, only say that the methods work, and you have to trust me on that. Look in the thesis. So, summarizing, the thesis has formalized the conservative linear unbiased estimation problem. Also, an analysis of the different properties of conservative fusion methods have been made. At last, in the two conference papers, communication efficient decentralized estimation problems have been analyzed and solved with good performance, but with reduced communication load. So for future work, we will continue to work on this sort of unifying framework for conservative estimation problems. Also, more specifically, we will analyze the restricted best clue and the best clue and see, for example, if they are actually the same in some cases. And that's all I had.
So with this, we thank Robin for his nice presentation, and we will take a 5-minute break, and when we resume, Dr. Noack will start his questioning session. So, welcome back, and now I'm going to hand over to Dr. Noack to start the questioning session. So, please, Dr. Noack.
Thank you very much. Thank you for having me here. It's an honor to be the opponent. It would have been great to be in Linköping, but yeah, now we have to do it in a virtual form, but I think that will work fine. So I would like to start with a very general question. I think a few aspects of this you've mentioned already at the beginning. So as a motivation, you used like object tracking. Let's suppose we have multiple independently operating sensor systems which produce estimates. Could you explain again why we will have to deal with correlated information in this case?
Can you take the question again?
So we have multiple sensor nodes which operate independently, but still the information that the sensor nodes provide could be correlated in some form. So could you explain again why we have to deal with correlations and why are they present in such a sensor network?
Well, the presence, as I said, both depends on measurements being pre-processed into estimates. That's one part. But also, I mean, the major part, I think, in decentralized estimation problems is that you have this communication of information. So if I send my information to you and you send some information back to me, if I use that information, I would probably double count some parts. And that it can be seen as some kind of logical fallacy. Of course, you can't use the same information twice.
Mm-hmm. And if you have two sensor nodes which run like two Kalman filters and they haven't communicated before, could there be still some correlation?
Yeah, it would probably, because you have this effect of common process noise. So as they are observing the same target, the target has the same process. So hence the two estimates will become correlated.
Mm-hmm. And why is it difficult to keep track of possible correlations? Like, to keep the information that could be double counted or something like that?
I mean, if you need to have a lot of memory to either keep track of each individual measurement and also to keep track of all the cross correlations if you use estimates instead. And I mean, if you have multiple nodes, you would need such much more memory. So that's the major thing. Also, I mean, if you have heterogeneous platforms, they will have different systems. So, I mean, if not all the systems keep track of the cross correlations, then you will end up with this problem of having unknown cross correlations anyway.
Mm-hmm. So if we do not know the correlation, then we cannot compute the best estimate in the blue sense. So we have to compute something suboptimal. And maybe the simplest way is to use naive fusion, simply ignoring the correlations. And we still will get an unbiased estimate. So in any way, even if we use a conservative method or not, we will get some suboptimal estimate. So why do we care so much about conservativeness? So what is the benefit? Why do you need conservativeness?
I mean, if you have completely unknown cross correlations, then you can either use this, I mean, as you said, a naive approach, but then you end up with the uncertainty be underestimated. And I think these estimates at a later point will be used in some kind of decision making, at least for my applications or our applications at Saab. So if you have, I mean, underestimated severely the coverage about a target to shoot down, that could have really fatal consequences. So then it's a better way, of course, to overestimate the information, or overestimate the coverage of the target.
Yeah, exactly. For further processing, you will need a proper assessment of the uncertainty. So there are already a few methods presented, like covariance intersection, inverse covariance intersection, and other methods for conservative fusion. So what do you think are still the missing pieces, or why is still intense research necessary?
You mean intense research in conservative methods? Well, for one point, I don't think there's, which I speak of in the thesis, that there is no unifying framework for conservative fusion methods or conservative estimation problems, like it is in the classical case. So it would be nice to sort of unifying not only the different conservative methods, but also to unify it with the classical linear estimation case, where you have full access to all cross correlations.
Maybe we can start with the first part of your thesis, where you discussed linear unbiased estimation and fusion. So the first thing I would like to know is why you adopted a Fisherian view instead of a Bayesian view, because most of the applications will deal with Kalman filtering and prior information and stuff like that. But you said at the beginning you will confine yourselves on a Fisher's view.
Well, one part is that unbiasedness is not so well defined in the Bayesian setup. But maybe the major reason was that it felt like a much easier way to approach the problem, to use a Fisherian view than a Bayesian view. I think it's more intuitive to think of state as, true state, deterministic state, instead of random vectors.
So would it be dangerous for a Bayesian to apply your methods then? Or could he directly adopt the techniques?
No, I don't think so.
Okay, so there's another question I would like to ask, and I will just quickly share my screen. Do you see the slide? No?
I don't see it.
Maybe no. Probably now you will see it. So actually, these are figures I took from your thesis just to have these figures as a foundation to discuss the general principles. So on the left side, we have estimators, like 2 sensor nodes, these two. And on the right side, we use some kind of fusion formula to combine the outputs of these 2 estimates. So I'm just concerned, or I would like just to know whether this procedure, like first doing 2 estimates and then doing the fusion afterwards, is the same as collecting all the measurements that are here, the input on the left side, and then doing a single estimator, or then applying a single estimator to these collection of measurements, whether this would be the same as doing this first independently and then doing the fusion afterwards. What do you think?
I am not sure, actually.
So we can assume, for instance, that the measurements are different from each other. So there is no, like they are independent, and they are like the subsets of measurements are not overlapping.
I think it would be the same, but I'm not sure in this case.
Yeah, actually, in this case, it should be the same because they are independent. And actually, the reason why I asked this is because, as you have shown in your thesis, the structure of estimation and fusion is very similar. You can both can be defined in terms of a least squares problem. So you combine them together in a single least squares problem, in this case at least.
Yeah.
Yeah. So maybe as the next part, I would like to discuss the conservative estimation. And as you have shown in your slides, you use a restricted version to like make the problem solvable somehow. And you also mentioned that you might lose some information in doing that. So you're not, and at the end of your thesis, you also mentioned, the presentation, you also mentioned that maybe in both cases you get the same result. Could you explain this in more detail? Or what is your feeling? Do you expect there will be a gap between the best clue and the restricted best clue, or will it be the same?
First, I think for the largest ellipsoid method, they are the same. That I'm sure of. But I'm not sure about more general, coherence intersection, inverse coherence intersection. So I haven't been able to prove it. But I think it will, you can prove it. But I'm not sure, because I haven't been able to do it yet for a general case.
Yeah, I think that would be great, because the restricted clue is much easier to address than the other case, as you said. Regarding the conservativeness, there are differences between like the optimal estimate, the naive estimate, and the like conservativeness. And maybe you can also discuss this here. So this is also a figure of your thesis, and there we have some differences in the ellipsoids. So we have the best estimate, which is this dashed line, and then you have the naive estimate, which is smaller. And then you said, okay, there's some kind of a relationship. If you would compute the covariance with the actual gain of the naive estimate, then it will be larger. Does this relationship always hold that we see here?
No, it does not always hold. You can find some weird correlations that make the second inequality does not hold.
Okay. So which part of
I would say in general it do holds that inequality.
Is there a part of this inequalities that will always hold, or why do you think it does not hold in some cases, this relationship?
Well, I mean, the naive will not always be smaller than the blue one in the positive definite sense. In some cases, you end up with this problem of comparing incomparable matrices, which I think that happens when you have kind of weird cross correlations in the R matrix. I have found some examples on that at least. But in general, it do hold.
Yeah. In general, the true or the possible blue covariance matrices could also fill out these gaps here, right?
Yeah, exactly.
Okay, there's another question. You also had this example in your thesis, and the nice thing about this example was that you have defined a unique covariance bound for this example. So I wonder whether this can be generalized to, like, say, block matrices. So let's say all these blue and green parts are two-dimensional square matrices or something like that. Do you think something like this could still be possible to show, like, that this entire matrix has a unique covariance bound where A and B are somehow unknown?
Yeah, I'm pretty sure it is possible to do that. We have been working on some, block methods instead. So consider like the block version of the largest ellipsoid method. So you can do that. I'm not sure in the general case though.
I mean, you had also some counter examples where you have your additional dependencies.
Yeah.
You also, it is very useful if we have a unique.
No, I think we lost him again.
A unique minimum covariance bound.
Sorry, Benny, we lost you a bit there.
Okay, I'm sorry. It's about can you hear me again?
Yeah.
It's about the uniqueness of the minimum covariance bound. And you mentioned something in the thesis like if we have a unique minimum covariance bound, then there can still be multiple best clues. Can you explain this in detail?
You can have different, at least in theory, different gain matrices K, but still being able to find the same covariance matrix. So if the gain changes, but still the same conservative bound. I have no idea when it would happen, but at least theoretically it can happen. So then the state estimate.
Does it also hold?
The state estimate will then differ, but the covariance matrix will be the same.
Does this also hold for the restricted case? If you have a minimum covariance bound, could there be still multiple best restricted clues?
In that case, well, according to this conservative version of the Gauss-Markov theorem, which I proposed, then I think the solution is unique. Yeah, it should be unique in that case.
Because you can
if the conservative bound is unique.
Okay. And then, so the next step was that you applied this idea of conservative estimation to conservative fusion. And the most prominent example is covariance intersection. And you have shown some properties of optimality for covariance intersection, something like you cannot squeeze an ellipsoid in between that is smaller or something like that. Does this really prove that covariance intersection is the best you can do for unknown correlations? Or could there be something else still possible?
I mean, in my proof, I only show that it is the restricted best clue. But I've seen other papers that shows that given that the cross correlations are completely unknown, then covariance intersection is the optimal conservative estimator.
Yeah. So for covariance intersection, you use the parameterized family of estimates. And for each possible like bound like this, like parameterized bound, there's no other ellipsoid that is smaller. Could there still be some other ellipsoid that is not in this parameterized family that could be smaller?
No, I don't think so. Not in the assumptions I do in that proof or in that case.
Okay, yeah, in the proof you have the family parameterized by this omega scaling. I just wonder whether there could be some ellipsoid outside this family that is incomparable to each ellipsoid in the family, but is still smaller somehow.
No, I don't think it is possible to find any smaller, given the assumptions I make in the thesis.
Yeah. Okay. I also have a question regarding the inverse covariance intersection for partial estimates that you have introduced. So could you, so this is I think a very useful generalization that you have proposed there. Could you explain what these matrices G really means?
Yeah, these matrices, they in some sense filter out, or what to say, mask, filters the allowed cross correlations or the allowed correlated information in this case. And they are necessary to be able to guarantee conservativeness of the partial estimate form of inverse covariance intersection.
Do you have any like applications in mind where you also can then define such a matrix G, like in a multi-target tracking scenario? Do you have an idea how it could look like in this case?
It could look, you have to, I mean, for a cert, say that we have, well, we only deal with two estimates, so C1 inverse and C2 inverse. Then if a certain agent has this C1 inverse, in this case it should be able to calculate this G1 in that case by comparing the correlated information from a previous time point with the information at a later time point where after some measurement information has been added to the estimate. But I don't think it is possible for a certain agent to always find this matrix G for other agents.
So is there so what was the idea to define like this projection in the information form and not in the like original state space where it might be easier to see like how this projection should look like?
Can you take that question again?
Because this matrix G is now applied in the information form. So I think it's supposed to pick out some specific parts of the common information. So why didn't you define it in the state space instead somehow? Like not in the information space, but the state space. So there's some estimate gamma that is common to all these.
I think I tested that as well, but it was more intuitive, or I don't know, maybe also necessary to work in the information domain in this case. And I think that has to do with that inverse coherence intersection assumes this decomposition which is in the information domain.
Mm-hmm.
So I think I had to constrain the allowed cross correlations, or the allowed correlated information directly in the information domain.
Mm-hmm. Okay, no, interesting. And then you have shown something like this that is necessary to show that like you will obtain a conservative estimate. And this looks quite complicated to prove in practice. So I just thought, like if you have a multi-target tracking scenario and you have many objects that need to be tracked and you have different sensors, and each sensor maybe tracks a subset of these objects. And another sensor has a different, possibly overlapping subset, then probably this matrix G here can pick out the parts that overlap and something like that. And it might be very useful in this case. So I just wonder whether it is sufficient to show this for the like full state space. This is the original assumption for inverse coherence intersection, as you have also demonstrated in your thesis. And whether then, after like restricting it to a subset, you can directly maybe prove the right-hand side or something like that. Have you thought about ways to find simpler ways to prove it on the right-hand side?
I have tried some version of that you suggest here. I didn't got it to work, not if you have to be very stringent. But maybe you can do something with that. Mm-hmm. But I didn't manage to, at least.
Mm-hmm. So that could be some part of future work then.
Yeah.
To simplify this part. Okay. Then if we come back to this example and we think about like something like this, that this block belongs to like the first estimate or the first sensor, and this block belongs to the second sensor. And then you have these type of correlations where A and B are not known. So what fusion method would you suggest in this case? What would be the best way?
Largest ellipsoid method, because we already have the component-wise aligned cross correlations. So, which means that the first component of the first estimate is only correlated with the first component of the second estimate. Mm-hmm. So that was meant by component-wise aligned correlations.
And what are the general requirements to apply the largest ellipsoid method?
Sorry, the general.
So what are the? So this is a very special form of a covariance matrix, and maybe could you explain again what the general requirements are to apply the largest ellipsoid method?
The general requirement is that after some kind of transformation, so I maybe can write on the board. So after some transformation, joint transformation of this joint covariance, you get something that looks like so. You only have non-zero elements on these parts, on the diagonal of the block matrices. And if it looks like that, then you can be sure that the largest ellipsoid method is conservative.
Mm-hmm. And then can you think of like situations in practice where you have this kind of special structure?
I mean, in the vast majority of the case, you won't have this kind of structure. But I think it is interesting to see when you have this structure approximately. So maybe if you have some, say, some sensor that provides a diagonal information or diagonal covariance matrix, and also when the process noise is a diagonal matrix, then you could possibly get something like this.
Mm-hmm.
But that's like only works in theory, I guess. But instead, looking when this is approximately satisfied, then you can be pretty sure that largest ellipsoid method will provide a conservative estimate.
Mm-hmm. What do you mean by approximately satisfied?
Say if this element root 0 here is like much smaller than those parts on the diagonal.
Okay. Mm-hmm. Yeah, I studied the derivation of the largest ellipsoid method, and what I find very interesting is how the assumed cross covariances look like. Like you derive this D12 for the joint bound, and maybe you can comment this again, like because this already the joint bound has a very interesting structure with respect to the off-diagonal blocks.
Can you be a bit more precise?
So what I mean,
is there some page in the thesis I can look at?
Actually, what I mean is that you, I have it here. It's like 71. Like for each off-diagonal element, you consider the individual single elements. Like it's the formula 4.62.
Yes.
And you take the minimum of the two elements, let's say. And then if you consider the largest covariance bound or the largest ellipsoid covariance bound in the next formula, these off-diagonal elements are already the fusion result, aren't they? So you have the transformation of T times T, or the transpose of T times D12 times the inverse of T. And this, I guess, should already be the final fusion result of the largest ellipsoid method, which would then imply that the off-diagonal elements already contain the optimal fusion result, or the largest ellipsoid fusion result.
I think if you follow this sort of scheme, did you mean that you also use this equation 464?
Yeah.
Yeah, in that case you would get the same covariance matrix as the normal largest ellipsoid method, but in general the state estimate would differ.
Mm-hmm.
I think at least.
Mm-hmm. No.
Because then you weight the different input estimates differently from what the largest ellipsoid method does. So the largest ellipsoid method only picks one component from exclusively one of the estimates.
Mm-hmm. And for the joint covariance matrix on the slide, what would be the fusion result then, or the covariance matrix of the fusion result with the largest ellipsoid method?
It should be the identity matrix.
Yeah.
I'm 1, 1, 1 on the diagonal.
Simply takes the minimum of the elements. I think that's very interesting.
Yeah.
Okay. As the next part, I would like to discuss the applications of your methods or ideas. The first one was the diagonal covariance approximation that you mentioned. And I just would like to know, how do you do the fusion at the receiver? So the sender prepares a diagonal covariance matrix to reduce the communication load. And then the receiver obtains the reduced information. So how is fusion then performed at the receiver?
I only have tried using coherence intersection for fusion. The methods differ if there were some kind of scaling at the transmitting node, or if the scaling has to be performed at the receiver node. But it is always coherence intersection. But I want to try it with the other methods as well. I just haven't had time for that. So.
Probably this is also very interesting if you know the correlations, but then do this kind of approximation with the diagonal. So how are the correlations affected by this? Do you have some kind of an initial idea how this will look like? Like whether you could still apply something like the Bartolom-Campo formulas, but one of the covariances is approximated by a diagonal matrix.
I mean, you could use that formula, I think. But then you have to make maybe some assumption about the cross covariance, like it being in the largest ellipsoid method, diagonal cross covariance matrix. But I know if you ask if the result will be conservative, I can't answer that. In general, not I guess.
Yeah. And I have a specific question regarding, like on the next slide. One of these methods is directly an adapted version of covariance intersection. Could you explain why we have this omega here in front of the estimate of the receiver? So this is the estimate of the receiver, and this is the information that we have from the sender, right?
Yeah.
So why do we have the scaling here in front?
Well, that's just the fusion rule of covariance intersection, and you need to scale also that part because that part could also be correlated with the things you receive from the other agents.
So I just tried to compare this with post-transmission scaling based on the dimension, where you use the dimension as the factor of the diagonal. So how does this compare to this? Because if you choose this W's to be like 1 like nx or something like that, shouldn't it be pretty similar in this case?
You can adapt the version, the method you call the dimension-based scaling method. And if you adapt it to be more general, you would get exactly the same result as this one. So if I show you on the board. I mean, so if you recall the figure I presented gave in the presentation, if this was the original C, then D would look like this, X is aligned. And I just scaled it like this. I just multiplication with D. But if you instead consider if you have the same rectangle and say that you just want to find any possible ellipse that encloses this, it could be also this, then you can parameterize this diagonal matrix exactly like the joint covariance intersection. So in this case I call it CI then. I should put an inverse. Then you get something like this. And if you use that parameterization instead, instead of only fixing this diagonal to n times the diagonal matrix and parameterize it, then you would get exactly that kind of formula.
So this method on the slides, the adapted covariance intersection version, is then like more general than the dimension-based scaling. Is that true? Does this statement make sense?
Can you take that question again?
Whether this the adapted covariance intersection method is a generalization or simply more general as the dimension-based scaling, in the sense that the dimension-based scaling is a special case of the covariance.
Yeah, exactly. So that's what will you get if you, in the formula you show here, if you fix all this omega I and just put each omega I as 1 divided by dimensionality, I guess it would be. Then you would get this kind of method.
Okay. Okay, thank you. In this chapter on methods to diagonalize the covariance matrix, you essentially mentioned 5 different ways to do that. So what method do you recommend? What is the best I should use?
That depends. If say that you already have this fixed data link protocol, for example, where you just transmit directly the diagonal elements from a covariance matrix without scaling. So we are not allowed to scale or something. You're just allowed to send these diagonal elements. Then I would use this adapted CI method, which you show on the screen. If not, I would go for the eigenvalue-based scaling method.
Okay. How difficult is it to do this eigenvalue-based scaling? So what, just use the eigenvalue, or is there something more I have to consider? Like it's just scaled by the eigenvalue, or is it more complicated to define?
Yeah, it's a bit more complicated. I mean, you first transform the covariance matrix into the correlation matrix, and then you find the largest eigenvalue of the correlation matrix. But I described the methods without transforming into the correlation matrix, just because I thought it was easier to interpret it.
Yeah. So I would have expected that the optimization-based method would be more accurate, or more would provide a smaller bound than the eigenvalue method. Yeah,
me too. I don't know if that has something to do with all the symmetries of the problem or something.
So what kind of objective function did you use for the optimization-based?
I use trace, as I use trace for the optimization of covariance intersection as well.
Okay, interesting. Because maybe because there are also the eigenvalues involved. Maybe this will lead to the same result or something like that.
Yeah,
it'd be interesting to study that.
Yeah, that's true.
And I have another question about this approach, or this idea of reducing the communication demands. So what other methods do you think of could be used to reduce the data that need to be transferred about the estimates?
Well, one method that I've been thinking of lately is having some kind of, I don't know, event-driven communication. So if you, like in this paper about the information selection methods, then I used this, I constructed some reference information or reference covariance matrix. This matrix in some sense represent the information that the remaining agents of the network use or has access to. So if I plot this information, and then I have my own information matrix, which perhaps looks like this. Then I can compare this and check in which projections do I have more information than what I think the other agents does. So in this case, it would be in this direction. So if I have more information in some direction, then I transmit that information to the other agents.
Mm-hmm. So this is now the information extraction method, right? Essentially.
Yeah.
Mm-hmm. What I just had in mind is some compression techniques or quantization or something like that. What do you think about these ideas?
Yeah, that's of course very important, at least, I mean, for real applications to consider quantization effects, but we haven't considered it yet. Mm-hmm. Our data compression is more, I would say, like high level or on a high signal level or something.
Mm-hmm. Okay. Yeah, I have also a few questions regarding the selective information extraction method. And you started to illustrate the idea, and you've also illustrated it in your presentation. So, and let us maybe first check, or I would like to understand first, what is the information that you really send to the receiver? If you have selected some parts, you said in your thesis you will send this this type of information here. Maybe you could you explain again how these terms look like?
Yes. So in this case, I mean, first you make some kind of eigen decomposition, and then which would look something like this, maybe verse there. Then I pick out, for example, if this D inverse looks like this, and we say that the first element, they are order, so this is the largest, then the second column. Then I can sort of picking out first this US is represented by say if I want to pick out two projections, then I pick out the two first columns of this matrix. Mm-hmm. So this would look something like, well, n elements here and n elements there. Mm-hmm. So it would be a n times 2 matrix. And ds in this case would be just like that. Mm-hmm. So okay, these two parts are the only thing I need to reconstruct the information.
Mm-hmm. So I try to illustrate that here. So you have just picked out two columns and then the compressed or the smaller version of this diagonal matrix. And then finally you get a matrix like this and will transmit it instead of the full square matrix. Is that right?
Yeah, exactly.
Okay, and then you mentioned in your thesis that at the receiver, you still have to split it up into U and D.
Yeah.
Based on the knowledge that these are unit vectors in U. But I just wondered whether you could simply take the square here and then multiply these, making from this the full square matrix again or something like that. Or any other term way of square root decomposition. Instead of separating it again at the receiver.
Yeah, you can probably do that as well, I think. Yes. And just to be clear, if you pick out, say, like in this case, two columns, the two projections, then you don't need to transmit all the elements of the second, because if this is U1, this is U2, you know that this is an orthogonal matrix, so the inner product of this should be 0. So you don't have to transmit all the elements, you can just solve some equation and find find the last element, at least in this case.
Okay. That's interesting. So there might be some ways to still further compress the information somehow. And so this is the foundation of this method you described. And then you showed these two different ways to like keep track of some kind of information at the receiver. So the sender has this additional part here to keep track of this information and then decides what is the most important information there. So I just would like to know first, what are the requirements regarding the communication links? Do they have like, so how often do they need to communicate, like for the different methods? And is this the bidirectional communication in each? If there's a data link established, will there be a back and forth communication or something like that? So maybe, what are the requirements for applying this method?
I don't have any such requirement. I mean, you can transmit, and you can transmit any way you want and as often as you want. But for this conservative method, there's no reason to transmit information that often. Because you won't have been able to extract any new complementary information.
So I just wondered about the received information method. So if I want to select information that I want to send to another sensor node, then I first need to receive its information, right? To be able to like extract the information.
Yeah.
So how, because that requires a lot of communication then again. We can comment on that. So what I mean,
what was your question? Is how you initialize this filter, or?
Or what happens if I do not get the information from the second sensor node? So I want to send some information out, but first I need the information from the other node.
Yeah, I haven't studied that case where you have either some loss of information, but I mean the method should be degraded in that case, because it's based on what information you have received. So you need to have received some information to have some clue about what the other agents have access to. But maybe a workaround to that problem would be to combine these two methods, the transmitted information method and the received information method.
Actually, that was one of my next, or maybe even the last question, how to combine these methods and what would be the benefit, especially with respect to like the communication rate with respect to the processing rate at the sensor nodes. So how could a combination look like?
A combination could look like that in this, say in the TI filter that I call it, if you also fuse information, that you have received in that filter, then you would in some sense have combined these methods. But I guess, you want to wait at least this part that you received, because if you have say 10 nodes, 10 agents, then you would receive much more information probably than you transmit. So I think you need to weight them against each other in some way.
So would it make sense that if there is a data link, then I simply replace the TI estimate by the RIS, or by the actual estimate, as it is done here? And if I do not have a data link, then I do this recursion here.
Yeah, exactly. You can do that as well.
And what happens if if each of these sensor nodes is connected to multiple nodes? How do you keep track of the information? Because then do you need multiple of these C head, or how do you do it?
I don't know if you actually need to keep track of all. I've used the information using coherence intersection in this case. So that would, in some sense, ensure conservativeness of also this reference covariance, C hat.
Mhm. Yeah, what I mean is if you have possible multiple nodes receiving information from you, do you need for each of these nodes an individual C hat?
Oh, okay. No, you don't need an individual C hat, but you do need an individual C hat if you have multiple targets
Mhm.
that you observe and estimate, but not just because you have multiple nodes.
Okay, but the receiving nodes, each of the receiving nodes could have like different sensors and different information. So
Yeah, that's true. You could do it a bit more advanced, but it should work doing this as well.
okay, then I think it's I have been asking a lot of questions. So maybe the last question now. So what extensions do you have in mind of your work? You already mentioned a few ideas at the end of your presentation. But for instance, if you want to derive a new conservative fusion method, so how could it look like?
I don't know that yet. I mean, I think it's a good start to formalize this unifying framework for conservative estimation problems. And after you have done that, then you can maybe get more intuition how you derive a new conservative method. So therefore my primary research in the following will be around this unifying framework.
And what about like trying to design network topologies where, like, I don't know, correlations are not present or can be ignored or something like that? Would that be possible?
Yeah, it's always possible to do that, at least in theory, to design some kind of centralized sensor network. But I mean, for example, for military applications, since centralized sensor networks are not so robust and critical to nodes, it's better to go with this kind of decentralized sensor networks.
Okay, and thank you very much. So these have been all of my questions.
So, thank you very much, Dr. Noack, for very good questions. And with this, we will open up for the Zoom audience to ask questions through the Q&A function. And I believe we already have some questions, and Fredrik will read up these questions to Robin.
Okay, so my name is Fredrik Gustafsson, main supervisor of Robin here, and it's still time to write some quick questions in the Q&A link here. We have one with 2 questions mark. So the first question is, how would you explain the concept of information to a lay person?
Yeah, maybe it's best to just so if you have covariance like this, it has the uncertainty in these directions is pretty large compared to this. So how we define information is just the inverse of covariance, which is the inverse of the uncertainty. And then you would instead get something that looks like this. So in this case, you instead have just a small amount of information in that direction that you have a large variance. So I think that's the best way to understand the concept of information. Yes.
The follow-up question here is related to the common sense word information that you use in everyday text and talk. What is the relation of this arrow here and the usual concept of information?
Well,
the longer arrow, the more information, or?
Yeah, in the information domain, the longer arrow, the more information, because in the same direction, in the covariance domain, the longer arrow means larger variance.
And the concept of gossiping in spreading information on the Twitter, for instance, how is it that relating to your work?
Gossip. Maybe it would be related in the sense that you reuse information when you gossip.
So there is a relation between the common sense information word and what you are doing here. So no open questions. So with that, I hand over to the chairman again.
So thank you, Fredrik, for reading the questions, and thank you for answering. And with this, I would like to thank everyone involved so far. This actually ends the public part of the defense, and now I will reconvene and meet with the supervisors and the opponent and decide about the grading. And after that, which will take a few minutes, we will get back here in this Zoom meeting and report the grade result. So let's thank everyone. Thank you.
Thank you.
So, welcome back, and after a very short meeting, I've come to the conclusion that I with pleasure would like to pass Robin. So, congratulations, you have passed.
Thank you.
And congratulations from supervisor.
Thank
Also,
you.
flowers from the department.
Congratulations.
Thank you, Benjamin. Very nice questions. And difficult questions.
Well, that's good.
Good answers.
Okay, so then I guess we end here. Thank you very much, everyone, for attending.